Well, folks get started here because I'm going to go to Dmitri right away. He's the most east of us all, I do believe. Wolfgang and Eduard will be next as we work our way west across the country. I'm going to start the meeting here. Okay, let's get this meeting started. This is Ted Klein. What kind of video do I have up? Maybe I'm not even here. Let's start this again. Let's see this thing. Yeah, okay, I'm here. Let's start this meeting again. Oh my gosh. Hi, everybody. I'm Ted Klein. Welcome to the SARA Drake's Lounge here on March 1st, 2026. Thanks for holding on and being patient here as we keep letting folks in. We are on many different time zones. So what we're going to do is start way off in the east, way off in Russia with Dmitri first, and then work our way west because Dmitri's up real late at this point, so he can join us. Dmitri, are you there? Can you tell us what you're up to?
Thank you, Ted. My greetings for all. I have today a short message from me with little presentation. Just a moment. See the screen?
Looks great, nice and big, and we hear you well. Go ahead.
Okay. This is about observations of recombination line, hydrogen recombination line from central parts of our galaxy, Milky Way, from central parts Sagittarius A region. A few common words about these regions. This is objects in the galaxy center, a supermassive black hole in the center. You can see the image from Event Horizon telescope obtained 7 years ago and published 4 years ago. This is image with accretion disk and center and shadow in center corresponding to black hole itself. Not very huge from supermassive black hole mass, about 4 million of solar masses. It is noted that our black hole was active, like active galactic nuclear some time ago, with luminosity about more than 10 and fifth of solar luminosity. And also in 2010, some Fermi bubbles was discovered in our galaxy in gamma ray and X-ray emissions. It's also they are seen in hydrogen 21 centimeter line. You can see this works of Felix J. Lockman from Green Bank. Many works in he is so this is a lot of work from him about hydrogen line from Fermi bubbles. You can see the reference, one of the reference here. About recombination line, united hydrogen is the central part is formed by radiation from O and B type stars around the center, not to black hole accretion. And combination lines expected are expected not to wide about several tens of kilometers per second. You can see work of you can see from this picture from this work and spots in H166 alpha line. It's spot about 1 degrees in west. Observations using a green bank 20-meter dish, beam filling factor not too high for this line spot and beam width of the dish and at these frequencies. System temperature I calculated is differs from calibration data from Skynet. I calculated the system temperature by oven, means background temperature about 60 kelvins estimated and can be polarized. background can be polarized. Air temperature about 20 kelvins, and I estimated spillover, dish spillover temperature about 28 kelvins. So total is bit higher, 100 kelvins. Calibration data is up to 20 to 200 kelvins. I used the next my value of system temperature. Results of observations. This is two polarizations. Tracking time 200, about 200 seconds. As expected, the line is not too wide, and do not wider than 10 to 20 kilometer per seconds. The plot in brightness temperature and antenna temperature was calculated using the system temperature and using beamwise and beam efficiency, estimated beam efficiency. Polarization's contributions to average is difference almost 2 times in peak values of brightness temperature. All results was obtained with high resolution mode of Skynet. Velocity resolution is about 3 kilometers per second. The difference I can explain only by a polarized background and possible difference in telescope temperature for X and Y polarizations. This is all for now. If some questions, I will be glad.
Great work, Dmitri. So I was just wondering, so I saw on your plot that the peak of the radio recombination line was at minus 20 kilometers per second. And I was wondering, do you maybe know why that is? Because you would expect that if you look towards the galactic center, that the peak would be at 0 kilometers per second, just like the hydrogen line.
This is even for all the data. This is not exactly 0. This is not exactly 0. This is even a bit larger than 0. But this is minus 20. What I obtained after post-processing probability of for these frequencies. This is close to 21 centimeters hydrogen frequency, and pi probabilities is low. I think this is really recombination line. What can I say? This minus 20 is really is reasonable is reasonable value for the center of galaxy. This black hole now is not active, very active in accretion, and I wouldn't expect higher velocities. This really about 0, and minus 20 is not too much deviation from 0.
Yeah, okay. Yeah, I was just wondering. It seems interesting to me because it implies that the ionized gas is moving differently than the neutral gas in the center of the galaxy. So it implies that the ionized gas is moving towards us. So it's moving away from the center. So, but maybe that's just driven by the, I don't know. It's just an interesting observation, I think. Great work.
No, thank you. Thank you.
Thank you, Dmitri. Other questions for Dmitri?
So I'm wondering if that slight negative velocity implies that it's an expanding bubble or something.
Okay, maybe.
Very good. Dmitri, thanks again for another wonderful presentation. We start there in Moscow with Dmitri. We work in our way west across the world. Well, usually Wolfgang would be next in Germany, but Eduard, don't go away. You're next. Then I'm going down to, Mark and then Andy. So, Eduard, speak for us. Tell us what's new.
Well, In terms of observations, not really anything new from my side, at least not from my own telescopes. Because, well, I've been quite busy with just generally just with work and with, yeah, the weather also hasn't been too great. And the few times that we had some good weather, I just went out with the optical telescope and just did some visual observations of Jupiter and the moon and that sort of things. So I don't really have any new like radio observations. What I did do is that I finished the last video of the Andromeda Galaxy series. So this was about a project that I did last fall on some hydrogen line observations on Andromeda Galaxy. So I finished the last video from that series. I'll post a link to the whole playlist in the chat, in the meeting chat in a minute. And also what I've last week I also visited the Astropeiler Observatory. So I spent a Sunday afternoon there with Wolfgang and Vanessa, and we did some observations of some water mazes, but maybe Wolfgang is going to present about that, or maybe not, but we just did some observations there with their 10-meter dish. So that was also quite nice. Anyway, so yeah, that's it from my side.
Thank
Any
you very
questions?
much. We're working our way across the world. Wolfgang isn't quite ready yet, so we're going off to Mark. Mark, tell us what's going on there in the UK.
Hi. Whoops. Sorry. Yeah, well, I've not got that much to report. I'm struggling at the moment with setting up this SuperSID system. I've decided to run it from a 12 amp lithium iron phosphate battery because I think from the small 5-volt rechargeable batteries, the maximum I could get was about 90 hours. So, anyhow, I've got this pretty hefty 12 amp battery now. But what I'm struggling with is connecting the battery to the Pi. I bought this Pi 02W, and I've been following a guy called Bill, I think it's Kunkler. He was running his from a solar powered or a battery on trickle charge from solar power, so it can go on forever. I don't have any solar power system, but what my question is to connect the lithium-ion battery to supply both the Pi and the SuperSID. I was going to use this splitter cable. Yeah. I'm just getting mixed up with the connections because for the SuperSID, you've got a male USB. For the Pi, it will be a male USB. That will go to the splitter, two ends of the splitter. And the other end of the splitter will be a male USB. And now I need to connect that to my 5-volt supply. And the 5-volt supply is coming from the 12-volt lithium battery with the DC converter. Thing is, I purchased what I thought would be a very low noise converter. It's something like, it's a few microvolts noise level, so ChatGPT says it's very good. But it will only supply about 500 milliamps. And that 500 milliamps has to supply the Pi Zero and the SuperSID audio amplifier. Does anyone know if that would be sufficient? Oh, also today I purchased a, what's it called? TC66 USB connectable meter. So I'll be able to measure what currents are flowing.
Do we have any SuperSID aficionados here today
Can you
that
see
can
that?
help out?
I bought this little USB connectable meter.
And
Yeah.
that gives the status of the USB
It'll give
connection,
you
I guess.
it'll give you power, amps and volts. It's bidirectional. I think it's pretty amazing.
Yeah, I have
I
several
got
of
it.
those. It's very accurate, and
Yeah.
it tells you what the amperage is, and what is your total volt amp requirements for the Pi? 2 amps is more than enough, and for the
2 amps. Wow. I could never get 2 amps from this
I'm saying that
DC-DC
it's more than
converter.
enough.
No, I think he said he could supply up to 500 milliamps, and the Pi Zero only needs about
Yeah.
200 milliamps. And
I
your
bought this.
SuperSID probably only requires about 100 milliamps. So you
This
should be okay with 500 milliamps.
it's a low noise amplifier for DC converter for marine applications. It's got a few microvolts noise. But it only supplies 500 milliamps.
And,
Well,
and we
that
think
should be
that
enough.
should be enough.
So you could measure what your requirements are,
Yes.
with your meter. So just measure your Pi and then measure your SuperSID
Yeah.
separately. And just as long as you stay below your 500, you should be okay.
I'm just struggling with the connections from the battery to the SuperSID and the Pi. From the battery, I was going to connect this sort of power barrel connector. Then I've got to feed that to a USB. Yeah, it's got to go via USB connection to the Pi and the SuperSID. Does that mean I've got to start soldering wires onto a USB connector?
Well, you need a way to get that connection made. So you could, there are different ways to connect the power to the Pi. You could use a USB connector if you buy a cheap cable and cut it, and so that you can access the wires and use them to connect to your battery. And then you could plug in that USB connector and supply power in that manner.
Yeah.
Why only half an amp? Why is your power supply only half an amp?
I don't know.
Why would you
This
limit yourself like that? You don't know. Get something like a two amp power supply. They're very inexpensive.
Well, he was focused on trying to get a low noise contribution
Yes.
from the supply. And so he's
Yeah.
probably got one that's got a regulator that's limited to 500 milliamps, but yet gives you a very low level of noise, which is a good thing to be trying to do, especially in the noisy environment he lives in.
Yeah. That was on the advice of ChatGPT.
As you go up in current, you usually suffer from more noise in
Yeah.
regulators.
Is it worth me showing what the output at the moment is on my SuperSID so you can see what sort of it tends to look like?
Yeah.
We're ready for that, Andy. Go ahead.
I don't know if it'll help, but here we are. So that's the SuperSID here currently.
Mhm.
And that's a pretty normal trace that I'm getting. That's using its bespoke software, which just records a spectrum every 5 seconds, I think it is.
Okay.
I
That's
actually managed to identify a couple of solar flares on some measurements a couple of weeks ago. And I was just trying everything out with phone batteries, these little 5-volt, 10,000 milliampere hour batteries. But like I said, they only last about 90 hours. It's the maximum I got. And
How about
they're,
buying a bigger one?
they're very problematic because because the SuperSID consumes so little current, the first battery I got kept switching off. It's got an inbuilt protection. So I had to buy something called Keep Alive. So it's a little
Put a
connector.
resistor in parallel so it wastes a bit of energy.
It gives a pulse apparently every however many seconds. So the battery thinks that it's consuming a large current, but it only worked on specific types. Ansman. That's why I decided to go to this lithium-ion battery because I don't want to go every 3 or 4 days and restart the system. It would be really inconvenient.
Mm.
I'm not sure we're the best place for information on SIDS. There certainly is a Google.
Yes,
Google
I'm
groups
active.
and all, but
I'm in contact with this guy, Bill Kunkler.
yeah.
He's sort of helping me out.
So, Mark, I'm not sure we're coming up with answers here for you on SuperSID.
I'm sorry, I've got nothing amazing to present.
All right.
Like
That's
I
an
said,
outstanding question, but this will be listened to
Yeah.
by other folks on the recording, and I encourage them to reach out to you and give a hand.
Yeah, appreciated. Thank you.
Ted, can we give it a try with my audio? Can you hear me now?
Ooh, Wolfgang is back, sounding great.
Yeah.
Yeah, I think we're complete with Mark here at the moment. Wolfgang is next, and then I'm going to Andy, but I'm not sure where Steve is, what country you're in, so I don't know. Let's go to Wolfgang, then Andy, please.
Okay, thank you, Ted. Let me try to share my screen. My trouble that I'm having today is that the Zoom app doesn't want to start. And hold on.
We see no activity yet.
Yeah,
Ah,
I have to.
I see blinking.
Yeah.
We are patient.
It's a mess today. It doesn't want to show. So I'm afraid I have to do the full screen share. And then, does that work now?
We see all the little pictures down the left-hand side, but yeah, we see your pretty pictures. Please go ahead.
No, you should see a presentation now.
Yes, we do, with the little previews on the left.
Okay, so then, is that okay now?
Full screen, perfect. Keep going.
Okay. I'm not sure whether you're actually interested in this, but I just want to share that adventure we had recently, and I called it a low noise amplifier open heart surgery. And the story is the following. We are using a set of very low noise LNAs, and some people in this group will know that, but just for your information, we were fortunate to get a set of LNAs, 2 LNAs for both polarizations, which were designed by Sander Weinreb and she from Caltech. And we are very grateful that we were given 2 of those to us. The characteristic of this LNA is that it has an extremely low noise temperature for a ambient temperature device. So it has a noise temperature of 8.7 Kelvin. The gain is 38 dB. And the key element there, why it is so good, among a couple of things, is the device which is shown here. It's where it's pointing. That's an indium phosphide high electron mobility transistor, which is manufactured by a Swiss company. And that is a extremely low noise device. And in order to keep it low noise, this is not packaged. So it's a chip, and the chip is directly bonded onto the circuit board here. So this is the device there. Okay, so that's, I would say, the key ingredient why it is such a low noise system. And what happened, unfortunately, is that one of these LNAs failed. So we went into looking into that, why it failed. It became fairly clear that there was something wrong with this first stage here. So we did an inspection under the microscope. And well, this picture is not too good because I had to actually take my mobile phone and go through the eyepiece of our microscope. So it's not very clear, but I think you can see that one of the bonding wires had detached. So there are 3 bonding wires. This is ground, this is the output, and this is the gate of the transistor, the input. So it was clear why it didn't work anymore. So we were desperate and we cried for help, because it's something that we cannot do ourselves. We don't have a bonding machine, and in particular, we don't have the experience. And fortunately, and I'm really grateful for that, a group of people from the Fraunhofer Institute, which is close to us, that's a very high-tech institute for high-frequency physics, as they call themselves, and radar techniques. they offered to help us with that. So I went there, and this is how it went. First of all, they have a better microscope with cameras attached and so on. So this is our transistor as it was then. So you can see again the detached bonding wire, and you also see that what they call the bonding foot, this is broken. So that's where it got detached. And then there was some further inspection of it. This is a even higher resolution picture of our transistor under polarized light. And again, you can see the detached, or the part where the bonding wire was. And then they went ahead and did some test bondings and so on, and rebonded that. So this is what it looks after that. Now, as you can see, this is the foot of the new bonding wire, but what had happened was that this piece from the old bonding got displaced a bit. So we were a bit concerned whether there would be any contact over here, but that was inspected later on and everything looked fine. The other thing that was done, they were a bit suspicious about this bonding connection here. They said, okay, that's still contacting, but it may break loose also. So they attached an additional bonding wire to ground. So this is again a new bond over here. And then we did another detailed inspection of this part here. They measured the distances and they measured the vertical separation because it's not at the same level as here. So everything was fine. We decided not to do anything about it. We could have tried to remove that a bit, but the risk was too high. But I think this is a very nice picture of the transistor that we have. You can also see a little bit over here, that's a little bit of dust, but that doesn't hurt because there's a passivation surface over it. And it also shows nicely the size of this transistor. So it's a 50 micron across roughly. And so that was attached. And of course, I immediately went back and went into our lab and checked how the LNA was working. And this is what we have. So we have, again, 38 dB of gain. We can't quite measure the noise figure. Our noise figure meter is not accurate enough to actually measure it. You can see it shows a negative noise figure of minus 0.1 dB, which is, of course, physically impossible. But we know that we do get that measurement if the LNA is okay. So we are back in business with our amplifier. And we are very grateful, first of all, of having those devices. Second, we are very grateful to the Fraunhofer Institute for helping us with the bonding. And that's sort of our adventure from the last 2 weeks. Okay, thanks.
Wolfgang, back up 2 pictures if you can,
Yep.
even in this mode. What is the dimension again across one of those units?
Well, this is the actual transistor that's shown here. And you see the scale here.
Oh, they're down at the bottom.
There's a scale of 100 micron. So I guess it's about 50 micron across.
All right. You're always hard to top, Wolfgang. Oh my. I thought my problems were bad. Well done. That's exciting. And you found a great friend. That's even locally. That's perfect.
Yeah. All right.
Thank you for sharing that. Questions for Wolfgang, please.
I can make a couple of comments about it. The thing that's interesting here is that they use what this is called wedge bonding. When you have this flat ribbon like this, sometimes thermal compression ball bonding is used, but for RF, usually wedge bonding is done. And that line that's formed right down at the bottom of the wedge is where the weakest point is. So it probably just broke that loose from handling, I guess. You maybe jarred it and caused it to break loose on the one that broke. And the other thing, go ahead.
Yeah, we are not certain how it happened. There's a bit of a background story. We had to open the device because we had some instability. And the recommendation was that we should replace one of the capacitors there, which we did. But we were aware that this is a very critical point. We shouldn't touch anything there. So the people who did replace the capacitor. They were very confident they never ever got close to that transistor, but it may have been part of that handling that caused it.
Right.
So we're not 100% sure what really caused it, but definitely it broke at the weakest point of the wedge bond.
Mm-hmm. And if you back up a slide where you showed how it's in the package, in the whole amplifier package, one right there. What's interesting here is it's a strip line design where you're going from the input connector, and then this is a line that's been set up to be probably a 50 ohm line, but it could be some other impedance because the input to the transistor is another impedance. But then the bond is made directly to that line, whereas in a lot of packages that we use, that connection is going to go through another connector or some other interface. It causes an impedance mismatch. But this design of this amplifier eliminates that because you're bonded directly to this 50 ohm strip line when it comes in. And that's what I think really gives you that coupled with the high mobility of this indium phosphide gives you the performance that you want.
Yeah. I mean, certainly Sander Weinreb is the guy to talk about it. For those who don't know, Sander is with Caltech, and I think he's in his 80s now. And I don't think I would exaggerate by saying he has developing low noise amplifiers for radio astronomy for essentially all his life. I think he made his PhD on that, and I mean he's a guy who really knows these things in and out. And maybe as an addition to what you just said, one of the design tricks I would say is the matching, the impedance matching, because as many people know, not necessarily do you get the lowest noise figure by 50 ohm matching, but by some other matching. So I think the trick here is that it matches well to this type of antennas. And that's why we get a very good noise figure. What we did notice when we changed the LNA from our original LNA to this one, the improvement was more than we had expected just from the noise figure of the amplifier. So it shows it has even better matching. Anyway, so this is essentially the story behind it, and I'm just so happy that we got this fixed.
And then one more thing I wanted to ask or comment on is if you move back up to that HP noise figure meter that you were using.
Yep.
So on this meter, I happen to have one of these too. You can go down and push that button on the bottom right that says increase, and it will take averages. Do you do that when you take these?
Do that. Yes.
Yeah.
And
so this reading is an average of a bunch of readings, and it's still negative.
Yeah. I mean, what we do when using this noise figure meter, we let it run for a couple of hours to warm up.
Yeah.
With the noise source attached, we do the calibration several times until this is typically about 0.02 in that range and remains there. So we're really very close to zero with the noise source attached. And then if we put the amplifier in between with the same noise source, we get a negative reading. I think what happens there is that really the difference in the gain also changes a bit, what is shown here. And we are really, I mean, this noise figure meter is not specified to do something like an 8 Kelvin low noise amplifier. It's just what we do with this is just a sanity check rather than anything else.
Yeah, and if I could make a comment here too, I'm working on this preamplifier now myself, and I'm making measurements just like you're doing here with the same meter, and I'm getting 2 dBF. It's reporting in F, which is noise figure, but it's reporting in my case 2, and the device is supposed to be capable of 0.1. But I know I put it on the wrong substrate, and I know I have impedance problems, so I'm a long ways off. So it shows you how difficult it is, I think, to get these numbers to go down and to have a real good low noise source like you have, and how important it is in radio astronomy, I think, too.
Wow, this is great. Now, Wolfgang, this is the first amplifier, so it's got to be up near the feed on this large antenna you have. So all of this is floating up in the air. So this required folks on ropes and everything else to go up and fetch it, right?
Yeah, that's correct. It's obviously it's in a prime focus, so people have to go up there. And it's actually even worse. I don't have a picture right now handy. What we need to do is we have to bring the low noise, the receiver box with a feed horn down into the apex of the dish. But then we need to bring it over the rim of the dish down to the ground in our lab. And that's typically an exercise for half a day with 2 people climbing up with climbing gears and a couple of people helping with an electric winch bringing down the receiver box. So it's quite an exercise. We don't want to do it too often, but this time we just had to do it.
We all dream of big dishes, but oh my, it's an exciting life. Fantastic.
Yeah, I mean,
I think of this tiny itty bitty thing way up there and all the complications to make it happy again. Well done. And so what's the schedule to put it all back together again?
it's up there.
Oh, wow, terrific. And
Yep.
off you go.
Yep.
Other questions, please? Wolfgang, thank you very much for all that. Oh, we got one.
Wolfgang, little questions. Do you estimate losses in capacitor in the input, and the input lies in input microstrip? It looks long and have significant losses.
Yeah, if I understand your question correctly, the capacitor that we changed was this one up front here. Before that,
capacitor may have losses, and microstrip looks like long and may have losses too, and can reduce the noise of amplifier at all.
yes, of course, you have to be very careful with the type of capacitor you put in there. It has to be a very low ESR capacitor. And the reason why we had to change that, every now and then we had an oscillation, so the LNA became unstable. It started to oscillate at around 200 megahertz at a fairly high amplitude. Then, of course, that screwed up everything. And that's something that we discussed with Sandy and his team, and they knew this effect, and they recommended that we should replace or change the value of this capacitor. So it has to, that was the work that we've been doing on that unit. So it was far away from that. And actually that did the trick. So we don't have any tendency of oscillation anymore. And of course, yes, every component in here contributes to the noise to some extent. So if you don't have a low ESR capacitor, then your noise will go up. The reason why we think that all the changes that we did not change or did not worsen anything in the characteristic is that we achieved the same overall system temperature as before. Does that answer your question?
And here I thought that capacitor was small. Yeah. So well done. We're up to 1 hour. Wolfgang, thank you much for that overview and presentation. We'd love to see another presentation of you folks climbing the ropes and everything else. I bet there's pictures too. We want to see you climbing the rope. Yeah, that would be good too.
I don't do that. I'm too old for that, but we have some guys who can do that.
We appreciate their bravery. Well done. We're up to 1 hour already. We're going to keep marching along. I think we've gotten everybody out of the US except for Andy, please. Andy, tell us what's going on, and then we'll start working alphabetically down this list, which means Bob. Bob, I'm going to pick on you after that. Andy first.
Okay, nice to see you all, guys. And okay, so a couple of things which might be a little bit of interest regarding the SuperSID a little bit later on. But let me just start with this. So I decided to eventually do something over the last few weeks that I've never done before, which is going to sound quite amazing given that I have a UK Radio Astronomy Association VLF receiver for SIDS. For those that don't know, SIDS, SIDS, stands for Sudden Ionospheric Disturbances. These are changes that you can pick up on your receiver as a result of solar flares and various other things hitting the atmosphere and affecting transmission of very low frequency signals through the atmosphere, through particularly the ionosphere, because it changes the amount of ionization that you have in that level. These signals are coming in somewhere between 15 and 40 kilohertz, so they are extremely low and around about the same as a sound card on a computer. And for this reason, many people, including people in this group in the past, have talked about how they've quite successfully done this by just building an appropriate antenna and then feeding the result of that straight into their sound card. The SuperSID that was mentioned earlier essentially uses that same principle, using the sound card effectively as the receiver, but has an amplifier between the aerial and the sound card, so it amplifies the signal. Whereas the UK Radio Astronomy Association's device is a little bit more complicated and a bit more expensive as a result of that, in that it is actually a standalone radio receiver which can be tuned into a particular frequency. So therefore, it only works with one signal, but it theoretically can give you a better quality result. Anyway, that's what we're starting with, and I'll tell a little bit more about that as we go along. So I decided to have so I've got one of the UK RAA sort of tunable receivers, and I also have one of the SuperSIDs. But I thought I'd have a go at trying to make one of the ones that feed directly into the sound card. And because somebody else has been telling me about their success with it, and I'd seen some of their traces and thought, wow, they look fantastic. I thought it's an interesting question about just how much extra you get by trying to use other sort of tunable receivers, etc. When maybe the signal itself can be just easily picked up using the sound card. Anyway, next slide. If I get it to work. Right, so this is what I ended up with. Now, as this is my third VLF aerial, I suffered from the same problem that most of us suffer from, which is aperture fever. So I decided to make a bigger one. In fact, I was going to make a 2-meter one, but then I realized I was trying to make this indoors and I couldn't actually get it through the doorway. So I had to cut it down. So this is what ended up as 134 centimeters, which is that size there. You can actually make them as big or as small as you want. Many of them are only about 70 centimeters. And things like SuperSID, that's sort of probably 70 centimeters to a meter is probably about the standard sort of size that people make. As you can see, it basically involves a wire which is put around the cross, your wooden cross or plastic cross or whatever you happen to use. And this wire is enameled copper wire, so therefore it's electrically insulated. And you're talking about a spool of about 150 meters of this stuff, which is about 500 grams worth, or about $30 or $40 if you were buying it, 30, 40 pounds if you're buying it over here. And as you can see, you wind it around. Now, the wavelength of these very low frequencies is somewhere around about 20 kilometers. So even at 150 meters of wire, or another way, 134 centimeters on the cross, we're talking about a tiny fraction of the wavelength. So there's no attempt here whatsoever to try and get resonance on these aerials. But so get one of these, and then you probably see at the bottom, then you can sort of scrape off a bit of that, or use a bit of sort of steel wire to sort of scrape off the bottom bit of enameling, and then just solder it onto some other wires, and then essentially fit it to go straight into your sound card or whatever other device you're using. So this is a block diagram, because it's got one, oh dear, I think I've lost it. Come back, my block diagram. Because it's got, a couple of extra components put on there. So we've got that loop antenna that you've seen on the left-hand side that's just been made. I talked about the computer that this plugs directly into. In this particular case, the software I'm going to jump to on the right-hand side, which is the red box. There are various types of ways that this can be displayed. The UK RAA uses Radio Sky Pro to display the signal. The SuperSID has its own bespoke software, but in this particular case, I was interested in having a go at using Spectrum Lab, which I've used for a long time for meteor detection and display. But I thought it was a nice idea of having a user of this. So that's what the other person who was showing me their results had been using. So we'll come back in a second to the advantages of Spectrum Lab. But I want to just point out the capacitor that's there. It's worth noting that some sound cards, if not quite a few sound cards, don't like shorting across the sound card, or the connector that comes into the microphone input on the computer. And therefore, if you stick a little bit of a capacitor on there, I'm using a 10 microfarad capacitor here. It successfully takes the DC direct shorting out and allows AC through, i.e. lets the RF still go through to it. The other problem that I had is that in the past, many of you will remember that I've described how I use old i5 mini PCs that I pick off eBay for not very much. Unfortunately, it turns out that their sound cards are not very good. And so I couldn't get this to work with the not very good sound card that was on the little mini PC I wanted to use. So I bought again, not very much money, but just off Amazon, one of these USB sound cards. And this had the advantage that I could buy something that was a 96 kilohertz bandwidth on it, which was very helpful for this exercise. So let's move on to the next one. Now, in Spectrum Lab, which I will show you a little bit more of in a second, this shows setting up the channels. So what I haven't mentioned so far is the potential advantages of this direct input, or for that matter, going through SuperSID. I would say SuperSID has one little annoying feature, which is you collect the data and then you have to take it off separately to plot it. Whereas the nice thing about Spectrum Lab is you can access the plots very quickly. But there's advantages and disadvantages to everything. With these plots, the UKRAA one, because it's tuned into a particular frequency, you're therefore only picking up one station. Whereas with something like this, that is a broadband receiver, essentially across the whole of the bandwidth of your sound card, there is the potential, and more than potential, the actuality that you can collect multiple channels at the same time. Now, of course, many of these channels are coming in with approximately the same sort of power levels or signal levels. So therefore, we need to have some way on the plots of distinguishing the different channels from each other. And so on the left-hand side here, we've got the title actually is the frequency of these particular VLF stations. By the way, for somebody who doesn't know, these VLF stations are in fact nuclear submarine transmissions, or at least ground-based transmissions to nuclear submarines. But we're obviously not interpreting what's in the signal, we're just looking at the power effect as solar flares hit the atmosphere. So where it says expression, this is an opportunity, as you can in Spectrum Lab, to add in an expression which will actually change the value that is plotted on the chart, which allows you to then spread the charts out from each other, which as you can see I've done on the right-hand side. So that's me setting up the various channels so that the stations can be defined apart from each other. And down the bottom, it rather neatly gives me some labels. And so I tried this for the first time on the 25th of February and was rather pleased to successfully pick up some solar flares. We can compare them to the GOES satellite data, which tells us where the flares are. And just this first flare here that was occurring at around about 7:30 in the morning, you can see that we've got several different channels all showing a change at the same time. And that's one of the great things about this ability to actually record multiple channels simultaneously, is that, as you can see from the actual background data, there is a lot of variation in ionospheric signal strength. And if you can pick up several stations which are in different directions from where you're situated in your VLF radio station at your Radio Shack, then you sort of, that triangulation allows you to demonstrate that whatever's happened is a global effect on the ionosphere, and then much more likely to be due to a solar flare. This one, assuming it is a solar flare, which is the GOES data certainly suggested, demonstrates that you can pick up things which, if you looked at any one of those channels on their own, perhaps it would not be obvious that was in fact a solar flare. This one is perhaps a little bit more obvious as solar flare. You can see it's a slightly stronger C-class flare. This is 3.2 as opposed to the previous one, which was 2.6. And you can see now we've got a more obvious bump occurring. And this is now demonstrating a bit more of the standard shark spin pattern of solar flares, where they shoot up and then drop down more slowly. The other thing that's worth saying is, for those of you who've got more physics background than me, which is all of you near enough, you'll understand more about nodes and antinodes, and how therefore, as a result, sometimes these channels that you pick up, your solar flare goes down, other ones go up. And yeah, that's about as much as I know, and you'll understand more why that is actually happening. Maybe Eduard or Wolfgang one day will explain it to me. Here's another one, 3.9 flare this time, perhaps a bit less obvious, but you can see there's at least 2 channels that are showing an obvious change, and the other 3, there's some element of change. Again, very handy to have the GOES satellite to compare to. Okay, so that was, here's another one that's much more obvious, being an M-class flare, demonstrate why at 4 o'clock in the afternoon. All of these were on the 25th of September. Of course, I have picked a day in which there were quite a few flares deliberately to show off the kit anyway. But you can see there's much more pronounced changes in the signal there. But it also shows very much how the background can vary to such an extent that it's quite handy to have several different channels to compare to triangulate those results. So nothing came through on the 26th, and there was nothing in the GO satellite. And then I'm just going to finish off just showing a couple that came through on the 27th. Importantly, because one of the neat things about VLF monitoring for SIDS is that there are other people who kindly put some of their plots online, and Lionel Laudet, who I think is located in France, has put a very nice website online called SID Monitoring Station, which allows you to compare some rather excellent traces with your own. And he's the one that kindly also puts the GOES detections on his own plots so that you can do an easy comparison. So I was able to compare with him and compare with my plots down there. So on the 27th, you can see another C3.51 with an obvious sharp spin pattern there occurring at about 1:45 in the afternoon. And then around about midday, we have an interesting plot in my mind, because the 20.9 kilohertz plot at the top seems to give a very pronounced signal, and yet this is actually a low strength C1.5 flare, which I don't understand why some of these flares seem to be more obvious on my kit than others, and they aren't always necessarily related to the strength of the flare as was picked up by GOES. But again, somebody might explain that to me one day. Right, okay, so again, that's just a magnified image of that one that was a C3.5 plot there showing the sharp spin pattern. And I wanted to compare here, as I said, I have one of the UK RAA receivers, and this is a radio SkyPipe plot from that same day, and I've circled there the two flares that were picked up. And what's interesting about mine is that on this particular day, I wouldn't say that the two flares were that obvious on my results, which is interesting. The other one is we seem to have what looks like a very obvious SID later in the afternoon, and yet it's clear from the other data that wasn't a SID at all. So very strange. It is quite interesting, by the way, the 23.4 kilohertz station, at least from the UK, if you pick that one up locally here, especially with something that tunes to it, you can pick up this dip that occurs between about 7 a.m. and 8 a.m. in the morning every day, where apparently they turn it off to check it's still working, which always worries me, that if they can turn off their transmissions to their nuclear submarines, but every day between 7 and 8 a.m., let's just hope that none of our potential enemies are aware of this, otherwise it'll be an obvious time to attack us. Okay, so that was the first thing I wanted to show. The second thing, which is where anyone's allowed to comment on that in a minute, by the way, but the second thing is, oh, by the way, before I move on to this, let me just perhaps just show you, where have I put it? Here we are. So this is actually a live plot from the Spectrum lab there, showing it come through, and there's a plotter. So that is actually an up-to-date plot showing the different channels coming through. And you can see this, because they're coming in different directions, there's different changes. The ionosphere, background ionosphere changes, which as we move into the night. But again, the fact you can triangulate across the channels very handily makes it much easier to pick up the SIDS. Okay. Right, so let's get rid of that one for a bit. Where have I got to? Right, so a couple of slides just to finish. And so perhaps somebody can help me. So I'm just trying to calculate the dimensions of a single cavity filter for 1420 megahertz. As I've probably come up with all the wrong measurements, I thought somebody here might be able to improve them. This is more theoretical rather than me trying to build one. So I started off with just the equation there, working out the wavelength of hydrogen. And a quarter of that gives you 52.8, which they seem to be rather important measurements when it comes to cavity filters. And I got ChatGTP to help me to try and draw a diagram of a cavity filter, which is what makes me a bit worried. So it was suggesting 6 to 10 millimeters width on the rod. I know that has been used elsewhere. M2 rod or M3 rod seems to be commonly used. But anyway, so perhaps we could start with that, and I'll leave that up and perhaps ask people whether they can tell me what sort of measurements they would expect to see. I know, Wolfgang, you probably were quite aware of this, but if anyone else who would like to contribute.
Thank you, Andy. Touching all kinds of subjects. First questions for Andy or comments? Andy was speaking of SIDS, which is sudden ionospheric disturbances, where we study the sun by looking at the sun's effect on the ionosphere, which then we're watching transmissions through that at very low frequencies, really low frequencies, just above the frequency for our audio hearing, but in electromagnetic waves. Wow. Okay. Thank you, Andy. All kinds of fun things to explore.
Okay. Thanks very much.
With that, I think we've gotten everybody outside the US who are staying up late for this show. We're working our way in time zones. And now I come back. Oh, no, a couple announcements. Let's see. The Society of Amateur Radio Astronomers here. We're going to have 2 conventions. The first one's coming up on March 21st. We had trouble actually getting location for all of us to meet. So this one will all be on Zoom, one day only on Zoom, much like an extended Drake's Lounge, just like we're at now. If you have a paper, we're eager to see it, a presentation of some kind. It'll all be electronic with you sitting at your house. There's no registration. But if you have a paper, that will be accepted up until it says March 18th on the website. Our website is radio-astronomy.org. So you are now informed. Come see you on March 21st as well. Well, now with that, after that, way off in August 1 through August 5, we will be meeting in West Virginia in the USA for the Eastern Conference. Now you know. Okay, we're going to do the US side. We're going to go down alphabetically. I'm just clicking on participants at the bottom and working our way down. Bob is the first, Conrad, then David. Bob, what's new?
Oh, not a lot new. I'm busily still working on a little project when I have time available, and done some testing. As I mentioned earlier, I do have a high noise figure, so I want to address that probably with another board spin with an Andrews type board material, which will get the impedance matching down and better for the device. And I got the proper gain. I did have some trouble with oscillation initially because I didn't have good grounding, and I got that resolved. But making some progress, and hopefully one day I'll get something worth trying out and showing. So that's all I have today.
Very good. We're eager to know what's going on there. Conrad, we want you to move your head to the side, show off your background picture, and then tell us what's new.
Okay, I bought a NanoVNA to test my Sawbird. And I want to thank everybody who responded to my questions on the SARA Google Groups. That was really very helpful. And my Sawbird is working very well for the hydrogen line. And it's nice to know that's working well, but unfortunately, our weather has been atrocious here in New England. If you let me share my screen, I'll give you a good indication of what it's like. Let's see if you could see this picture. This is what it was like last Monday. Can everybody see it?
Looks great.
Yeah, my observatory looks like a little snow cone. We had 30 inches of snow out there. It was pretty bad. So, it's going to be 60 degrees in about a week. So I'm sure all the snow will melt. And then I can get back to doing this. We might actually have a clear sky tonight, so I'm hoping to do a little spectroscopy with my optical scope. And well, that's all I have to report, and just hear it for spring.
We need snow out here, so I'm not so sure. Conrad, behind you, is that your data presented?
Yes, that's my data. Let me try and move over a bit. That's what I've managed to accumulate so far with my scope in a box, which has worked very well. And I'd like to add more data to it, as soon as I can get rid of the snow, I'm going to set it back up and keep going for a while. This is what I call the learning session, because this is my first real dive into radio astronomy. And then during the summer, I'll set it up and have it run 24 hours a day for as long as I can, and repeat the whole experiment again and get, I think, a much better picture.
Very good. So with a small antenna that you can pick up and move around, it might be a meter across. You can also plot the galactic arms as shown, the yellow one, and then off to the left is kind of a purple one in fainter. So from your backyard, folks. Thank you. Alphabetically, we're working down to David and then Dennis, I think.
Nothing much. I've just been slowly going through the CASA tutorials on the data reduction, and that's pretty much it.
Very good. David, and I think we're down to Jason after that. Are you waving your arms up there? Oh, I'm sorry.
I think I'm.
Oh, all right.
Yeah. Okay.
How come you're out of order here? I don't know where. Oh, Dennis is at the top. He's on. Sorry, Dennis.
It's all right. Yeah, I'm here. I'm sorry I don't have anything to offer right now. I certainly feel sorry for Conrad that you guys get yourself a real winter. And anyway, but that too shall pass. And nothing new here. So really enjoying everyone's project. So let me just hang on and learn some more. Thank you.
Thank you, Dennis. Good luck. Everyone's surviving winter here. Working down towards Jason, and then I think Pablo Rick.
All right. Yeah, I've been out of touch with you guys for quite some time, so it's good to be back. I just in January just passed the 1-year mark at this new job out at NRAO, so that's going well. In fact, next weekend they're sending me to Mauna Kea to a colleague, and I need to go out there to figure out what's wrong with the weather station at the VLBA site on Mauna Kea, because it's been having issues for about a month and a half, and we've been trying to, support the site techs remote, and it's just not getting there. We need to get eyes and hands on the hardware and figure out what's going on. So I get to go to Hawaii next week. But as far as my amateur activities, I've just kind of started getting back into it. My laptop that I've had for the last 12 years finally kicked the bucket, and I had to replace it. So I'm actually on my replacement right now. That's what I'm using for this. And it was a refurb that I got for, less than $200 on eBay. So there you go. But one of the things I did was I dismantled my dish that I brought out here last January. It succumbed to the wind, and so I've taken off all the profile rib members, but I'm going to reuse the base and the sliding ring. And I've done a new calculation for a new dish design with slightly larger diameter. I'm going to make it 3.5 meters. And I've also, the design tool that I built, back when I first started doing this. Let me share my screen here, and I'll kind of show you guys what I'm doing. I'm kind of in the theoretical phase on this for now. Let's see here, entire screen. There we go. So yeah, I have a tool that I've built in Excel that I use to design my profile, my parabolic profile, and then I just mark it out in pencil on plywood and then cut it out. But one of the things that I was doing was estimating how many segments I actually need to get an accurate enough surface, assuming that, whatever I use for my cover material is stretched taut. And so in between the profile ribs, it will be kind of not curved, but straight. And so the idea is, originally I designed it based on the idea that I wanted to keep the maximum deviation from the theoretical surface less than 1/10 of the wavelength. And that was kind of a rule of thumb. But then I kind of reworked this to do a little more rigorous calculation. And what I did is I kind of used the conversion from a ramp type waveform to an RMS value using the 1/√3 rule, and basically assuming that the deviation from the theoretical surface is relatively a linear function as you go from the rib to the center in between the two ribs. And based on that, then trying to figure out what the RMS surface error is based on, an arbitrary number of segments in the dish design. And then what I did then is compared that value plot and looked on, there's some theoretical work, a reference that I found that shows a plot of surface error efficiency as a function of wavelength. And what I found was that the peak error of less than 1/10 of a wavelength roughly is roughly equivalent to an RMS error of like 2.7%. And if you look on the plot, that's about the point where the efficiency hits 90%. So apparently that rule of thumb is targeting a 90% surface efficiency. Of course, all of this is based on, the theoretical best case. And, obviously there's other things that could affect it. But the other thing I've been doing is looking at, as I was building and designing and rebuilding my dish, a couple years ago, there was the exercise of using the sun as a source to kind of map out the beam profile of the antenna. And I was always wondering, okay, how much is that measurement off because the sun's not a perfect point source, but it's, a 1/2 degree wide, right? So I did some theoretical calculations, and surprisingly enough, the difference between a point source and a 1/2 degree source is like very small for a 5 degree beam width. This plot is showing a small section of the curve, the theoretical curve, around the -2.5 degree point, because I basically plotted it with 0 degrees at the center of the beam and then plus and minus from azimuth angles from there. I'm actually going to, just to show you what the whole thing looks like, I'm going to expand this out to the full scale so you can see the whole thing here. So we got, okay, come on. Okay, there we go. And then we'll reset this to minus 10 and 0. There we go. Whoops. So what I've done is just used let's see here. We got, let's do 1/2 dB here. Okay. So this is kind of what the theoretical plot looks like. And, at this scale, you can't even see any difference. So basically, I kind of proved to myself that for a small dish like this with a beam width of, a few degrees, the sun is more than adequate as a source to get an accurate measurement. The deviation caused by the 1/2 degree width of the sun is negligible. So anyway, that was surprising to me. I thought it would actually affect it more than that. So anyway, that's what I've been doing lately. Lisa and I have really been enjoying keeping up with Eduard's YouTube channel as he's been doing his series on M31, and I'm looking forward to getting my dish back in operation with a slightly larger aperture, and want to repeat my M31 and M33 and M101 drift scans again, see if I can get a little bit cleaner results. And, I've never done IC342, which is a nice one in between those as well. So So yeah, that's on the agenda for the next couple months to get things going there. So that's all I got.
That's all. Okay, well, good. That's quite a list. Well done. We're working our way down alphabetically. Next, I have Pablo, then Rick, Stephen, and then Steve, who's patiently waiting. Pablo.
Speaking of Eduard, which, by the way, the kid is a genius, and I watch his videos all the time. He inspired me as far as getting a new radio telescope. And I was thinking what we need, what beginners need, is a fully steerable, pointable radio telescope for under $600. And I think I came up with a solution, and I'm going to share with you the screen here. Okay, what we need is a capable mount. Now, I've used this mount here, the IXS 102 PMC, which is only $300, 300 US dollars, and it actually can carry up to 18.5 pounds. And it's got an ASCOM driver, and it's fully steerable. So we now need something off the shelf to mount on this, which I already have, and that would be the Discovery dish, which is only 2.5 pounds. It's $129 plus the hydrogen line, which is $109. So that would be a 110 and 130, 240 and 300, 540. And now we need something with an ASCOM driver to actually drive it. And of course, Radio Eyes has that. And Radio Eyes is $40. So now we're talking about less than $600. You can have a fully steerable beginner radio telescope that we can track, and it's off the shelf. You don't have to build anything. The hydrogen line LNAs, it's quite capable. In fact, I bought an extra one for my 2.1 meter dish, and it works better than anything I've built, including the Sawbird. And it's amazing how sensitive it is. So for less than $600, we can have a fully steerable. Now, there are a couple of problems. One, it's mounting, and maybe Eduard has an idea on how to do it, mounting this dish on this equatorial mount, and so I have to solve the problem. And the biggest problem is that this thing here has Wi-Fi and Bluetooth transmitter. Now, we can connect it via USB, but I got to find a way to either, one, turn off the Wi-Fi, or two, put a mesh cover on the transmitter here and quash the Wi-Fi signal so as not to interfere with the radio telescope. So that's what I've been working on, and if I can do, that's going to be a competition to the scope in a box, and it's going to allow people to have a fully steerable, trackable radio telescope. That's all I have. Let me stop to share.
Excellent. So you're starting to put all these pieces together. I'm a little concerned that it will be a big footprint on the sky, but we can see changes in intensity as well. So that's neat.
Right. It's to beginners, and you can point it to the big radio signals.
Well, excellent. Sounds fun. Keep going.
Okay, that's it.
Maybe I have a quick comment.
Comment.
Pablo. One of the things that is sort of a limitation of using this kind of mounts is they are not water resistant. So they can't be left out in the...
But I saw the absolutely correct. But there's a solution to that as well, and I saw it someplace else where you can actually build an enclosure with PVC tubing and a tarp, which people have already done that. And in fact, they have it fully operational in where Conrad lives in New England with all the snow and everything else. So yes. But the mount, it's also only 26.5 pounds, which means that you can bring it in and out of the garage. It's quite doable. It would be great for schools, high schools, for STEM, for showing people. It's portable, and it even looks like a small, big radio telescope. So even the visual would be appealing. to, so all of these things can be solved, Wolfgang.
Yeah, the second limitation, I mean, we've been working with all these kinds of things.
Everything has limitations in life.
Where the limitations are, wind is another issue. The wind load of even of a 1 meter dish is quite high. So if you have stronger winds, it sort of will jump around in the breeze.
I have 2 Discovery dishes, and one of them is mounted on a tripod here in Southern California, where we get winds of up to 50 knots. They're called the Santa Ana winds. No problems. Quite resistant to the winds. It's only 2.5 pounds, so that it doesn't have a lot of, and it's only 70 centimeters too. So the beam width is going to be gigantic, of course.
Yeah, I mean, it's just does the tripods remain where it is in the wind? So if you have heavy winds, you have to somehow to fix it to the ground. Otherwise, it's getting.
No, you don't have to fix it to the ground. I'm also a filmmaker, and I have sandbags, and I put a couple of sandbags on it, and it doesn't even begin to move. And there's a lot of wind here. So you can take it with you. You can mount it. You can set it up portable. You can put a little tarp construction. It's all doable and inexpensive. And it's not going to compete with the big scopes, but it's a trackable system, and it's less than $600 US bucks, quids, whatever you want to call it.
Cool. Keep exploring. Andy, your mic is open. Do you have a question?
Oh, no, sorry. I'll switch it off now. Apologies.
No, I'm just trying to keep up. Pablo, exciting. That's great. We're moving down to Rick. Rick is a member of the DSES. I'll show a picture in just a moment. And then Stephen, and then Steve. Rick, what's new? I call upon Rick, K0GD. He's busy, it seems. Stephen, you're next, and then Steve, please. Stephen, what's new? Stephen, your mic's open. I'm looking for you. No, you're no picture and no audio. Technical difficulties here at the moment. That means Steve, you've been waiting so long. Thank you very much. You're off on the West Coast. Where are you?
I am a neighbor to Pablo, who is my inspiration. So I also have a 10-slide presentation, if that's appropriate now.
Yes, please. Tell us. Cool.
I don't use Zoom very much, so I will struggle and may need your assistance. So
we've all been there. Yep.
Share. Let's see.
So many buttons.
Yeah. Google Chrome, is that what I'm doing?
Share, and then usually pick a window.
Uh-huh.
Yeah, right now we're seeing a Zoom window. Oh, maybe you can Alt-Tab yourself over to another window, or you have to back out and choose the correct window.
Let's see.
Alt-Tab. And the Alt key and tab.
I'm on a Mac.
Oh, boy. Okay. Let's back out. At least on Zoom, in our world, we share, and then you choose window, one of the tabs.
Okay.
And then you can choose which window you have already got up.
Share.
So maybe you have to jump out of here to reshare.
Okay.
All we see is the big word Zoom on the front.
Oh, yeah.
On a Mac, you get sometimes a problem where you have to say okay over in the settings to allow it to share a particular screen that you want to share. You have to give Zoom permission to access screens and share them.
Well, we're sharing a Zoom screen.
Usually it'll come up and tell you that if that's a problem.
If you just swipe with 3 fingers up, then you have all your open windows.
I tell you what, I think I have power to remove your sharing. Stop.
Please do. Here's the stop sharing button.
Okay, we win. Now try again, do a share, but Bob, is it you pick a window that already exists?
Yeah, he should be able to pick the window he wants to share, or you can share the full desktop and then just show us the section you want.
Okay. Let's
On this account, we learn Windows, we learn Linux, now we're learning Macintosh too. Oh, that's better. Different picture. Now I'm seeing an email kind of thing. A Gmail. Yep.
And then
maybe you can pick another.
This one?
Removing receiver, it says.
And slideshow?
Much better. Now
Better?
you found your way through the maze.
Okay.
Please begin.
So I'm a retired physicist. I've worked for 30 years in the aerospace industry. I've been lurking in the SARA rooms. You guys are amazing. I really appreciate all the great stuff you've been doing. And as I said, Pablo inspired me to do this project, which is to try to do a calibration of the Discovery dish by solar transit and use that to learn about radio astronomy. And from my experience in my career, I've always learned when I want to learn something new, I go back and I pull the journal papers from the time when this was a new topic, because the papers then explain stuff. They don't just assume you know everything. So on the left here, you can see I went and pulled a paper from the Aerospace Corporation, for those of you who know what that is. And it's on using the sun to calibrate L and S band telemetry links to satellites. And L band overlaps with the radio astronomy section. And I noticed also when I was reading through the journal papers, they were constantly referencing astronomy textbook by J.D. Krause on the right-hand side. So these were in the kind of early mid 60s. So I bought the book and I pulled the article, and that's what this is based on. And we're going to try to use not the sun per se, but the solar corona, which is much brighter. And in the 1.4 gigahertz region, it dominates as a source. Okay. So first off, you can hear me, right? I guess I should check.
We're looking good. We're looking the next page,
Okay.
hardware and software.
Thank you. So here's my kind of block diagram. On the left, I have a Discovery dish, which comes with the parabolic dish, the dipole feed, dual LNAs, dual filters. This is what Pablo when he read through all this with his excitement, I just saw, oh, I got to get one of those. It comes with all the coax and a little enclosure around the feed so it can be out in the weather. I added to that a adjustable in one axis elevation mount so I can literally just rotate two little hand screws and readjust it. It has like 13 different positions of elevation. A little wedge to put under it to give it a little bit more range that by moving the wedge, and I strapped it down to my air conditioner. I don't even have a yard, I have a little deck. When you add to the cost that Pablo mentioned about the dish and feed, essentially the mount and wedge and strap to put it on your air conditioner, it was up around $350. I used the RTL SDR version 3 for the software defined radio, and the cable from the Discovery just screws onto the end and it plugs into, and since TED, I had originally started also and worked through using the scope in the box from SARA with your EasyCall and EasyRA software. I went out and bought myself a Windows 10 desktop or laptop because I didn't want to fight anything new. And I went and downloaded SDR Sharp with IF average. So I didn't know, it took me a little while to realize that the software defined radio has a built-in analog gain. And so that's set at like 50 dB, which is a lot. And then under the laptop picture of Windows 10, which cost me only 150 bucks, you can get a Windows 10 laptop for 150 bucks these days off of Amazon. These are the settings I used in IF average, and I found a use for the delay between files. So I took essentially 1-minute collections for transit collection, and I also collected what was essentially Y factor data. So the hot, look at the ground, cold, look at the sky. And I took about 100 times larger integration times for them, which I'll talk to in a bit. And then for software, I wanted to see the numbers, touch them, play with them directly. So I used Google Sheets, which is free, Stellarium for planning, and for creating some of the data, which I'll talk to later. There's a VSLR calculator, which was mentioned in one of the SARA meetings. I used that when I was transferring the axes from frequency into Doppler velocity. And then, of course, I used the lab simulation software, which was first called the Wolfgang software, which I found fascinating, tracked it down, and used that to cross-check results. Okay, so as I mentioned, this is a three-part data collection. The first part on the left is essentially taking Y-factor data, where you look at the ground with your dish, collect hot 300, 290 Kelvin stuff, and then you look straight up and you take cold data. And instead of a minute collection, I'm taking like 100 minutes of collection for each of those. And I'll explain why later, because it matters. And then just did a solar drift scan where I waited for dawn to come up. I used stellarium to find out when I look straight south at the meridian, how high will it get the sun be in elevation angle, and then set my dish to that height so it will cross over and be going essentially horizontally, so moving only in right ascension and not, or in azimuth angle and not in elevation angle much. So, which for this test setup was 39 degrees. Then once I took that data set, and I only took 32 data files. So it was 32 1-minute collections of the transits separated by like 15 minutes, I think it was, because I decided I could get a lot of knowledge and understanding by taking a relatively sparse sampling of the data as it transits. So the first thing up in the upper right, of course, IF average gives you magnitude, which you have to square. So there's that to turn it into power. And so there's the equation in white just below that. And the curve on the left, which says P transit, is the actual power data, just raw, done nothing to it. And so you can see it has kind of the wiggly stuff that there was a whole lot of discussion in many of the SARA meetings about what was the cause of that kind of thing. And there's like half a dozen different methods, some used by EZRA, some used by IF average. Eduard does yet a different method for to correct stuff. So it's like there's a whole lot of different ways that people have tried to correct this. And so I'll throw my hat into the ring. And so I took the transit data and I used to create the green curve below, which is power 1. And that is simply taking that raw data and dividing it by the difference between the hot looking at the ground data and the cold looking at the sky data. So I'm actually doing a division, which is trying to correct a gain. So in my attempt, I presumed that all of the bad stuff in the blue curve, the wiggly jiggliness, is caused by gain variation versus frequency. And so that gave me the green curve, which you can see is got a big spike in the middle, but it also has everywhere where there isn't a big spike, it has a green slope on it. And so what I did was then I went back afterward and applied another correction, which is just a linear correction versus frequency. And just below it, I give the equation of what that is, where I just did a fit to the data to subtract off a linear gain correction, creating the red curve. Now, that large peak you see, that it turns out, well, I'll call it RFI for the moment, but it's actually hydrogen line data that when you do a very powerful correction, fairly good accurate correction on removing the responsivity variations, you can get surprisingly good hydrogen line data that just pops right out from the discovery dish. So then, as I mentioned, I took 32 of these 1-minute transits. And so you see 3 of them across the top here, the time I took them at, and I go to Stellarium and I put those times in because they're coded in the files that IF average, those times do. They're coded in the IF average file. So I go put them in Stellarium and I see what the solar azimuth angle was. So now I am actually measuring the azimuth angle I'm taking measurements as the sun moves in azimuth angle. And you can see 2 things in there. So each of these 3 curves across the top has the raw data. And the curve below it in red is the responsivity corrected version of that data. And so, and as you go between the curves, you can see, first off, the hydrogen is changing, which is kind of nice because you're actually moving in this progression across the top, you're moving towards the galaxy. So you're starting to pick up more and more hydrogen. But not only does the hydrogen line data change, but the DC offset of that data is also changing. And that's because the sun is a broadband transmitter, and it's pushing up both the blue and subsequently the red curves. And I then go in and I pick a part of the red curve, which I have circled in the three curves across the top, and I call that a subband of the full data, and I just take a average. So I'm trying to find the DC value in there. And so I'm actually, normally there's been a lot of referencing about people's data moving around over time as they collect data. And I just wanted to mention here that the sun, if you're going to take data for 24 hours periods, the sun moves through, and it's actually quite a bright source, which I'll get to in a bit. So anyways, if you take the DC values in those little subbands at those different solar azimuth angles and plot them below in the bottom curve, you're actually plotting the points. Those are the 32, that blue curve in the lower thing is the 32 curves. There's 32 data sets I collected as the sun moved across the sky. So I'm actually sweeping out the antenna pattern by taking the DC value from the curve. And now into the next one. So now I have a measured antenna pattern from which I can get a vertical height, so a signal response, which is just at this moment in something I call DN, digital number. So it's just some digital number. Most of the graphing that seems to get done is always in relative something or arbitrary units or something like that. And so this is my version of arbitrary unit, but I'm going to unarbitrary it in a bit. I can also measure the full width half maximum of the peak of the antenna curve, which for my data comes out at 25 degrees. And I can also find the center of the beam because I know I pointed it at 180 degrees south. The physical antenna, I pointed at 180 degrees south. It turns out that the beam is actually pointed not parallel to the physical structure because as also you learned that in electromagnetic systems, all metal, and even to a lesser extent, non-metals near the antenna tend to interact with it. And what it does is it pulls my beam 10 degrees further in azimuth from where the mechanical antenna is actually pointed. So that's something to remember, is that just because you point your mechanical antenna in some direction, the beam isn't necessarily pointed in that direction. Now I compared the data on the left, which is measured data, with the manufacturer's discovery dish. I believe this is a Fornek simulation for the discovery dish. Their simulated full width half maximum is 23 degrees. I actually measured it twice with the actual antenna, where, as Pablo mentioned, you can change the skew, which is changing the polarization of the feed. So I measured it at where the polarization was parallel to the right ascension and then also parallel to the declination directions. And it comes out that one is 25 and one is like 23 or 24. And they, in the Discovery Dish manufacturer's simulation, they got 23 degrees. So I was satisfied. That was pretty good agreement. By the way, they also note in their simulation that it's 0.3 degrees off of the mechanical pointing direction. And I believe that in Fornek, for those of you who do electromagnetic simulations, you can add the ground instead of having your antenna floating in space. And if you do add the ground, you have to tell it how high and what kind of ground it is, how high up, I'm sorry, how high the antenna is off the ground and its orientation versus the ground, because the ground will pull the beam away from the mechanical line of sight towards the ground. Now, they must have had it fairly high up and a ground that's not very conductive because it only pulled it 0.3 of a degree. So all right, so now I have measured numbers for an antenna pattern, which agree with the manufacturer's numbers fairly well. And to do the next step, I have to convert that into solid angle. So we often talk single direction beams in degrees. If you convert that into my 25 degrees into different angular units of radians, that's 0.44 radians. And if you assume that it's really circularly symmetric, which is close because I did measure it, that comes out that the solid angle it fills is 0.15 steradians. That's important later when you try to use the sun as a calibrated reference source. You need to know the solid angle of your antenna. And then measure the magnitude in the curve. You can see that's the delta P. That's just says it's 0.33 digital number, which I'm going to determine what that is. So now if you go, paper I referenced on the front, that's on the right is a figure one out of that paper. And you can use this figure if you know the number of sunspots on the sun that day, which there's a website called Space Weather Live where you can just go look that up. But it will tell you how much brighter the sun is than its normal quiet value. So normally the sun, if it has no sunspots, is about at 1.4 gigahertz, is about 100,000 Kelvin, which is crazy bright. And the reason is it's not the surface of the sun we're looking at the bottom of the corona. So which is, many people knows can get up to millions of degrees. But at this wavelength, we penetrate through the corona down to just above the surface of the sun, where when there's no sunspots, that's about 100,000 Kelvin. And the aerospace people found that the actual brightness of the sun at these wavelengths goes up with the number of sunspots. And so you can use this little graph to determine how much brighter the sun is. And I just did a little equation on the bottom, and it turns out with the 104 sunspots that were on the sun the day I took the data, the sun was effectively about 210,000 Kelvin. So again, super, super bright. But so once you have the sun's brightness temperature, you now have to scale the sun down because the effective brightness of the sun depends upon how much of your beam it fills. And actually, it's how much of your antenna solid angle it fills. If it's a well-designed antenna, the main beam solid angle is approximately the same as the antenna solid angle, which I've assumed. And so when you then, down in the lower left, you can calculate with the brightness temperature of the sun, the solid angle of the sun, which is about the half degree that Jason mentioned, close enough to use because the part of the corona we're using is so low near the surface of the sun, doesn't make the solar disk that much bigger. And then my measured M is main beam solid angle, which is approximately the antenna solid angle. The antenna solid angle actually includes gain behind the antenna and all kinds of stuff. And then you multiply that by your numbers of DNs that the signal moved. And you can now get a responsivity of how many Kelvin per DN number. So you can now use that number to convert your DNs, your digital numbers that come out in IF average, into Kelvin. And for the Discovery dish, that number turns out to be about 300, 290. So when you take that conversion factor and you apply it to the data, so I pulled one measured spectrum, which you see on the left for the Discovery dish, and I went back into my solar transit data and I just pulled one of the numbers out, one of the collected 32 files out. And that's at right ascension and declination of 18 hours, 28 minutes, minus 17 degrees declination. And you adjust now the frequency into your velocity in your local standard of rest, which there's the equation I use there. And that's the website, which several of you are using. And I saw also mentioned in the group chat kind of thing. So you get the velocity on the left and you change the dn on the vertical scale. You now get the curve that's there. And that curve peaks out at about 46 Kelvin above the background. And it has a slight velocity in the local standard rest of about 9 kilometers a second. And I also picked out a second little point where to the right of the main peak at 98 kilometers per second, there's another small 3-4 Kelvin thing. Then I went to the lab simulation and I put in the same location with the beam width for the discovery dish that I had measured. And so the curve on the right is the lab simulation's prediction of what a dish of the beam characteristics that the discovery dish has should provide. And so they come out with a very good correlation. 50 degrees Kelvin is what they're telling me I should be getting, and I got 46. And they said that the peak should be shifted off about 3 kilometers a second from 0, and I got 9. So, which is probably down to the limit of my ability to predict things and even know where the dish is pointed. So based on this, I'm fairly confident that the method for calibrating the brightness temperature numbers you get out of a discovery dish off the sun works pretty well. And now then I wanted to do a noise calculation. So I did that two ways. On the right side is essentially the Y-factor method. Since I had taken Y-factor data, I go through the calculation. I got a fairly high system temperature of 154 Kelvin, but I would say that's actually better than you are actually going to get out of the discovery dish. And the reason is I took a long time to work through, and it's really over on the left, which is if you take that conversion factor that we calculated a couple slides back of about 300 Kelvin per dn, and you go back to that subband of data, but now instead of taking the average, you take the RMS. You're now calculating the noise between frequencies. It's not within the same frequency band, but it's roughly right. You can now convert, I should say, the RMS DNs to RMS Kelvin, which is now the system noise in Kelvin for this 1 minute integration time files. So these numbers pretty close. And as Wolfgang was showing an excellent example, it's difficult to do noise numbers. I thought at first that these were just surprisingly close, but then I realized the radiometric number, which is actually 25% higher, the one on the left versus the one on the right, that the reason that is higher is because the method you use to remove your responsivity variations adds noise. If you did like IF average does, and you just take two files and you subtract them, you're going to get 40% higher noise because the noises from the two different measurements will RSS together. So unless you have a totally noiseless methodology for removing the responsivity variation, which you could make, you have to be very cautious to not inject a lot of noise by your methodology of trying to remove your responsivity. So variations. So anyways, that's just a little conclusion to that. Now, when you take this noise, even the system noise, the 0.2 Kelvin, and you go back to the curve and you look at 46 degrees, you're looking at, for that location in the sky, a 230 to 1 signal noise ratio, which is good. That's acceptable. You can do some pretty good work with that. And of course, that's only with a 1 minute integration. You can do substantially longer integrations to improve the signal to noise ratio. Then I had this one, I believe this is actually my last chart. So I had one last thing, which is people constantly look at small dishes versus large dishes. I know that's a constant thing that people trade in their mind all the time. So I wanted to take and do a little comparison of that. So on the far left, you see the actual data I measured at that location in the sky, that right ascension declination, giving me a brightness temperature of 46 Kelvin of background. And then in the center was the lab, again, simulation of that same location at 50, which, because I gave it the same full width half maximum, it's essentially modeling a 0.7 meter dish. And then I put in a 1.8 meter, I took a 1.8 meter dish, calculated its rough full width half maximum for its beam, which is about 8.2 degrees, so slightly smaller than 2 meter dish. And I went to the lab simulation and I asked it, how good would the signal be? And so here's the curve for a nearly 2 meter dish. I picked that particular size because that is the Marcus Leach paper, the CCERA picture that floats around also for brightness in the sky. That is the size of that dish. And it turns out that'll get you a slightly better, slightly higher signal to noise ratio at like 60 Kelvin or a slightly higher signal. And that's because the dish is, as Edward mentioned once, this is a single pixel camera and it's averaging everything together that it sees. And this particular spot in the sky does have a warmer part to it, but it also is surrounded by colder parts. And if your beam gets bigger, you average in some more of the colder parts. You also get some more of the bigger parts. So I just wanted to make this kind of caveat thing is that you can get similar performance from a very small dish versus a very large dish for radio telescopes when you're looking at targets that are what I would call resolved, which is a visible term, where the beam, the target completely fills the beam. If that's true, then you can get basically the same type of response curves for these different telescopes. And that's it. That's my presentation.
Wow, Steve, is that all you got? Gee whiz, that's magnificent. You say you've been lurking in our forums and reading things. We're just honored. You've been finding all kinds of great stuff.
You are another of my inspirations, Ted.
Oh my gosh.
Never seen a software guy just turn out so much software to try to make something possible.
That's magnificent. You had a whole adventure going through all this stuff. Magnificent. So I'm going to put a link in here, of course, for the SARA forum where a lot of you say you've been lurking and reading. There is a lot of information in there. I haven't read it all. And then going way back in history, and then as well as our webpage and stuff like that. So that's all great. We probably have many comments. Many of us have gone down some of the same path. And so we want to speak up. One of them is the sun is not a point source. So it turns out it's about half a degree. And I think we need to account for that too. So I think your 25 degree is actually 24 and a half. So it's even a little bit better.
And that's what I put it in. And
I'm sorry, I missed that part.
You can call it deconvolution. That's the fancy math term, which Jason was exploring deconvolution out by simply running the two cases to see that it doesn't matter. There's actually a mathematical function, and many of the visible astronomy software packages that people have, you can do deconvolution with it. And so if you wanted to take it out, you could. But now, of course, with 25 degrees, it's not going to make much of a difference. Right, Jason's much closer to where it starts to make a difference. And even he found it didn't make that much difference at his aperture size.
Well, and that result actually surprised me quite a bit. I thought it would have a lot more effect than it did.
It should do roughly what Ted said. It should add. It should, if you do it, because it's really the fancy math version is a convolution of the beam pattern with the source. which is
which I was kind of simulating in Excel by
Yes.
just
That's exactly right. Well, and you could figure out it's like, what was your beam width? 5 degrees? Was that? So
it was 5 degrees. Yep.
so you were pushing it up by 10% or something like that. And that's kind of hard to see, that's on the verge of mattering.
Yeah.
One more question was, at the very beginning, you said you found it on, what is it called? EarthQuest?
Google.
Oh, just plain Google. All right, good. All right, that's better. I didn't know if there was a website.
Sun solar transit as
all right, perfect.
Calibration or something like that.
Steve had a heck of a presentation. Other questions and comments, please.
Yeah, well, really great work. I'm really impressed. If you go back to your, not your last slide, but the slide before that, where you showed the different spectra from the lab survey, and you said that's as long as the source is very large, which is the case with these hydrogen clouds, it doesn't really matter all that much. And what you see indeed is that the peak of the hydrogen line is not that much stronger with the larger dish, but you can see that there's a bit more detail in the spectrum because you're resolving these smaller clouds a little bit more, but
because it's not uniform. You're right, Edward. If you look at the thing Ted has was it Ted? One of the software, maybe it was the H-line stuff. It has a little map in it, which was kind of a variation of the CCE, Marcus Leach's thing, and you can see there's detail in there. So it's it's kind of taking an average, but there's detail below the aperture. And I was going to do a chart actually where I actually took the cutout of that thing and put on the rough beam patterns on top so you could see the difference. But this happens to be, just a place where it doesn't matter. Now, if you're looking at a round little point source, like many of the things you're doing for your masers, that's a huge difference there. I mean, you just can't get around it. That's why I called it resolved. Whereas you're working on, many of your projects are unresolved. And
unresolved,
and I do want to do some of your galaxy stuff. Looks very tempting to try to take a run at with a small dish and see how good could it be. Now, I did know in your last video, you were showing 0.2 Kelvin brightness temperatures on your spectra for Andromeda. And I'm going, wow, that's a long integration time if I got a sigma noise of 0.2 Kelvin. So that's already a lot just to start to get anything visible.
I guess you got to start building a bigger dish.
I'll tell you, our illustrious Poobah, who was here earlier, Rich, with he wanted to do an electronically steerable array thing. I've been thinking about this.
Ooh, that's a very tricky one. Yeah, I'm always when I'm looking at interferometry, I'm also very tempted sometimes, but then I think I already have so many projects going on. First finish what I got right now. Anyway, thank you. Great work.
Excellent. Other comments? Or are you just afraid to follow up? Wow.
One comment here.
Dennis.
You should make sure Steve understands that as a SARA member, he might have an opportunity to use the green bank.
Big dude.
Well, yes. I've been watching, so I know that's an option.
Yeah, it was 2 years ago, I think. Wow. About a year and a half ago when I got back from the first conference I ever attended out at Green Bank. And as soon as I got back home, I got access to that 20-meter scope, and I was literally sitting at a local microbrewery having a beer and taking observations of galaxies from my phone. It was just I was like, I can't believe I'm doing this.
Yeah, I've got to say that I've done a number of those observations with Jason, and it's been absolute fun on the 20-meter, and not enough people do it. Your talk sounded absolutely marvelous. I understood about 3 words at the beginning, and then the rest of it went straight over my head. But hey, that doesn't matter, and it's just nice to be in that position. But certainly the 20-meter scope at Green Bank is well and truly open. And I know that SARA supports people doing interesting projects. We do have the East and West conferences coming up, and we're looking for people to speak at those conferences. So what you talked about here would be ideal, and what you might do on the 20-meter or anything else you do with your telescope would be brilliant. Just submit something for those conferences and give us some more interesting talks.
Very nice. Yeah.
I will say I was also inspired by Andrew's attempt at a phase array. So it was like, because this was the first one where he put it out in the snow with the two antennas. So I started thinking about it going, why doesn't that work? That should be
It
interesting.
would help if it pointed in the right direction.
Well,
I put it in my talks just to show.
so I'm working on, see, I don't have a yard even. I have a little deck. That's all I have. I mean, it's not even a big deck. And so it's like, I can't even get antennas far from each other. So I've already been thinking about how I'm going to deal with the fact that and my deck is rectangular and aligned north to south. So it's,
Oh yeah. Okay.
so, but
that's
I think
ideal.
I think I can work with that.
No,
How about moving apartment
I'm sorry. Oh,
to a bigger deck that points east to west?
in a different direction.
Well, the good thing about building a portable setup is you can go out somewhere and, do observations like out in the wilderness or something.
All kinds of great ideas. Andy, we need to get you a taller chair though.
Yes.
Oh yeah, you can't see us. You don't really want to look at me, do you? You really want to look at me?
That's slightly better. Maybe go back to where you were. Yeah.
I mean, you, I, and Dennis have got the best hairstyles. Oh, and Bob as well. There's various people around here with brilliant hairstyles.
Yeah. Okay. Sure.
People like Steve are no good. Want to get rid of him because he's got hair.
Any other presenters? Let me say this.
You
Very
haven't
good.
presented.
We're going to say this is the end of the video, just to clean that up. I'm still hanging around. We're going to chat for a while. Thanks very much. Marvelous show today, folks. And of course, get your papers in by March 18th, he says, to Dr. Rich for the Western Conference, which will be Zoom only, no registration needed. If you're a member, you get an email with the info. Thanks, everybody.
All
See
right.
you next time.
See ya.
Bye. Bye.
Bye.
Okay,